2025, right? And so I'm the chair of this session. I'm Zhongren Huang from Academia Sinica. So let me first introduce our jury members. So we have Professor Hong Zhenyong from Danjiang. And we have Professor Liu Yiyu from Taiwan Keji Daxue. And we have Professor Cai Zhisen, local. And we have Professor Zhang Zihong from National Synchrotron Radiation Research Center. Okay. So now it's your turn to introduce yourself. So let's start with the reporter. Here, reporter Teresa.
Hello everyone, we are the Variable 2 from KGHS. And I'm the leader of the team. My name is Wu Youshen. This is Nam Raojun. This is Wu Yichen. This is Huang Lejia. And this is Hui Yujing. Thank you.
Okay. So, Onan?
I'm the team leader of the Crusader, and these two are my best friend, Huang Shengchao and Zhuo Chen. And it's a great honor to have a physics debate with you today. So thank you, everybody.
We're teamed up. We're teamed up last year, and I'm the captain lead. This is Lin Xuanming. This is Wang Guanyu. This is Huang Yan, and he is Zheng Minhong. He might come later.
Okay. So I guess you know the last equation because of the net. Okay. Okay. So let's get started. So where is the clock? 对，他说等一下会过来。时间时钟。Okay. So now the opponent can propose the challenge to the reporter.
I'm going to challenge number 2, air muscle.
The reporter has 1 minute to decide. Okay. So all presenters, please write down your name on the blackboard. Now the reporter has 5 minutes to prepare. take the stage.
Good morning, everyone. I'm the reporter from Variable 2, and today I would like to report problem number 2, air muscle. This is the problem statement. Place a balloon inside a cylindrical net and inflate it. The net will expand and shorten. Investigate the properties of such a muscle, and I will focus on the parameters related to the stiffness of the air muscle. This is the theory. I would like to explain some of the notations here. F means the force the muscle generates, and R0 is the nominal radius of the muscle, while P is the inner pressure and epsilon represents the muscle contraction rate and is defined as the original length minus the length after the balloon is inflated, then divided by the original length. This is the next one. This is the second formula and the third. The notations are basically the same, but added the K is the stiffness of the whole muscle, and LS is the stretched length. And according to the paper, an air muscle is actually similar to a spring while it is applied a tensile force. But the difference is that the stiffness of a spring is decided by its material, and the stiffness of a muscle is determined by more variables. Next, the experiment. This is my experiment setup. The equipment includes an air pump, spring seals, a cavity, and other components. First, I pumped air into the muscle and inflated it. I record the process and measure the data. By substituting the data back to the formula, I can get the pressure, the inner pressure of the muscle. And these are the data I got: the force, the epsilon, and the pressure. From the data I got, and I could substitute them back to the second formula and get the correlated stiffness. With the correlated stiffness, I could calculate the related parameters too. And this is the force. Oh, by the way, the horizontal axis represents the time, and the vertical axis represents the force. And this is the epsilon, the pressure, and the discussion. By substituting the data I got into the second formula, which is this one, we can get the stiffness and then use it and other information to calculate the parameters too, which I need in this third formula. These are the results. And this graph right here is generated by Python with the relation between the stretched length, which is LS, and the inner pressure and the stiffness. You can see that the parameters relation with 0 here. This is the other. And although with different results, although the parameters are a bit different, you can see that the relation between 0 are all the same because the feature of the muscle remain the same. Here, I will explain more about the parameters because it might not be so clear. Q1 is bigger than 0 and is the natural material impact of the muscle to the stiffness. Q2 is bigger than 0 and it's the length impacts on the muscle's stiffness. And so it means that as the deformation increases, the stiffness will also increase. Q3 is smaller than 0 and it represents the length and the pressure impacts. Q4 has a positive correlation between K because it's bigger than 0 and it's the pressure impacts. Conclusion: the material has a positive correlation between the muscle's stiffness and the stretched length also has positive correlation. However, the stretched length and the pressure has a negative correlation, and the pressure has a positive correlation between the muscle balloon, so the stiffness will increase. This is all for my presentation.
Okay, so this is short presentation. We might just move on to next page. We can move on. Okay.
Oh, so hello. So first I'm going to ask about the page data. Yeah, it's this page. So I want to make sure. So first, the E represent. Can you explain why what E represents again? Oh.
Can I turn to the book?
Oh, okay. Okay. For sure.
This is the epsilon. It represents the muscle contraction rate. And
So-
this is the definition.
So in each time when you inflate the air inside, the contraction rate is different. Is that correct?
It will change.
It will change. Does it have something like a proportional relation, or is it?
When I inflate the balloon, the length will change, you know?
Yes.
The length after inflation. So, yes, it has positive correlation.
It's have a positive correlation. Okay, I got it. And it's the page 12.
Well,
This.
okay.
Yes. How do you calculate the force here? Or what does the force here mean? Is it the pressure, or did you?
Oh, it's the force of the balloon. Here, the force the muscle generates. Because when I inflate it, it has to become bigger. So the muscle actually has a force inside.
So it means the force of the net that pulls the object. Is that?
Pulls the object. Not
What?
really, because it will. How do I explain? Because the gas will push the balloon to
Yes.
become bigger. So
Yes.
there's a force that the muscle generates to
And what's its direct? Where is it? Its direction?
it's going inside the balloon.
It's inside the balloon. Okay. Can
It's
you
perpendicular.
draw it?
Here.
Because I'm not really clear with
Okay,
the pure
that
light.
is blackboard.
Sorry, time's up, so we need to move on to the next page. The opponent has 3 minutes to prepare.
Okay, hello judges and all the participants. I'm the opponent of the air muscle today, and I'm going to discuss with my reporters. So first, still, we are going to look at the phenomena. So the air muscle, place a balloon inside a cylindrical netting. When you inflate the balloons, it will exhibit a property like a muscle. And the first thing I'm going to say about, and I didn't really type on it, is I think the problem statement says that investigate the properties of such a muscle, but I didn't really think what he really exhibits a muscle. I see he used stiffness as a symbol of the muscles, but the things I want to see more is how does the stiffness change on the dependent parameter? Like if I change the size of the balloons, does the stiffness change the parameter on the Q1, Q2? It's just the impact on it, does it change? I think that's the topic we are going to talk about. And the next one. It's the pros and cons I see. So first one, I see his diagram she exhibits the different parameter he measured, but didn't mention how he measured it, which is I'm going to ask later. And second is the mathematical direction, I also said, and demonstration is clear, and, forgot to delete this. And the cons I have to say is I didn't see the real manipulation of the whole process, like how did she inflate the air inside, because he used time with force to make a diagram, and how did he manage to make sure that each time the air inside is at the same amount, or how did he inflate it? And second one, the conclusion I have to say it's, because I only see the calculation on the different parameter in the stiffness and force. So I think it's not really a conclusion of the experiments. And the third is the unknown manipulation parameter, like what I said, the force with the time, it's unclear because we don't know how did it inflate the air inside. And four is lacks of the discussion on the diagram. Like the force part, on the E symbols, it didn't tells us how did it really measure. Like, is it within the time you measure the change in length, or how is it? And the last one is lacks of the data of the motion of the muscles. Like, how did the muscle become flake, and when you leak the air outside, then what will it becomes? I think that's what I want to see in the air muscle. Next page, thank you. So on the theory part, she used stiffness to represent the air muscle, and also assume that the muscles presents like a spring. This is I'm going to ask. And on the experiments and the data, she mainly focused on the calculation of all the parameter, which is also I'm going to ask, how did she calculate it? How did she get the parameter? Okay, so I'm going to discuss with my opponents, reporter, sorry. Yes. First, can you still draw your models?
Well, I inflated the gas flow and they will also actually push the balloon.
Okay.
So the balloon will have a force against the force.
Is it the force is from the net, or is it?
No, it's from the balloon.
It's from the balloon. Okay. So
Actually,
it's
together the muscle, the whole muscle. Because the balloon has its force, it is
what does it mean by its force? Is it
elastic.
elastic force? It's a surface tension? No?
It is elastic, so it will have a force because it wants to retain its normal, its original shape. And also the net will limit it too.
Okay, so it contains two forces inside. First one is the balloon's elastic, and can you draw the all forces on it, like the pressure per unit, and he says the elastic force. Where is it Where is the direction of it? Like maybe in this part. Like maybe the pressure goes outside on this unit. Then this is the pressure, and maybe the elastic force is from this. Maybe from this part. Can you draw it like here? Like maybe also have a net force on it. Can you draw the whole force relation on this balloons on the muscles?
But I think you already do what I said.
So this is what you want to present in your equation, like your mathematical equation. Quotient.
The first equation.
Yes, this is what you want to discuss mainly.
No, I calculated
So how do you calculate it?
because I had the other one. The other
how did you calculate the contraction rate? Because from it says like when you inflate in a time, you calculate from here to another part, and this is the displacement. Is that how you calculate it?
Yeah.
So it's the whole length of the balloons.
Yes, it's this length.
So it's, how much is the time gap between the two displacements?
Here, the one I measured is here. Sorry, it went away. 2 seconds.
Nice. So I think it will be weird to see it has a lineage way at the beginning, because as long as the muscles grow, if the muscle begin like in here, and if it's going to be shortened, it will be harder to be, and because the surface tension has become bigger, right? Like here it becomes more, how to say, intense. But then the surfaces have more force on it, and so the tension just must become bigger, and it will be hard to move from one place, from the length to the width. Did you observe that? Like
If it goes this way,
yes,
the length stretch won't be that much.
yes, on each time, under the same period. Because you use time. Is that time?
If you look at this one, actually yes, because the nominal radius increasing will impact the length.
Yes.
So it actually didn't do that much.
So also, can you explain why in here it has a sharp growth and here it has a sharp decrease? Like what really happened?
Yes, you talked about this, this muscle, and because the nominal radius will increase,
Yes.
so the length will stretch down. And when it goes to almost the most, inflate to the most, and before it pops.
Okay.
And actually it's hard for it to keep.
Under the same rate.
Yes.
Okay. So next part I'm going to ask is, in your reports, you mentioned that you've seen the whole air muscle on the paper. It will be like a spring. Can you explain how do you think about it? Like what would you consider it to be a spring? A spring, sorry. Because still, like what we discussed, like if you push if the muscles inflates more, then it will be harder to be more wider. But for a spring, under the same displacement, the force you place on it should be the same.
Oh yeah, I talked about that because you know the spring, its stiffness is actually like constant.
Constant.
It's not a constant. It's related to itself, the material itself.
Yes.
But the muscle, I talked about that. The stiffness is determined by many variables.
Like what variable?
Like the stretch length
Stretch length,
and the pressure.
the pressure.
Yes, that's what I talked about. That's why I used the third formula here.
Okay.
Because the case. Yeah.
This is the case. Okay. So I just the last of my clarify. So did you really see the air muscle as a spring, or is it just your first assumption and you just push sorry away, or is it? Like the reason what is the reason you mentioned like it likes a spring, or what's the relation with the spring?
Because it is talked about in the theory, and they actually talked about the stiffness, and I'm curious why the spring's stiffness remain. A spring's stiffness will remain the same, but the muscle stiffness will change over time.
Oh, okay. So this is the reason why you talk about the spring. It's just because the stiffness. Oh.
Because that's what I focused on my report tonight.
Okay, that's I got your points. Then there is on the next part. Can I also ask about your manipulation? Like when I say, how do you inflate the air inside?
Let's go back to my experiment setup.
Yes.
Okay. I have an electronic air pump, and to pump air inside.
Where is the pump? Where's the pump in this picture?
Because I actually had a tube that goes inside. It's not just here.
Oh, it's not. Oh, so it's out of the picture. Okay. So this is how you calculate the force. You mentioned it. Like
Yeah, I had a spring scale. To calculate the force.
Okay, so this is the force and you inflate it. Okay, I got it. So the next problem of the page will be 17.
17.
Yes. So in these two pages, you calculate the different parameter of from Q1 to Q4, and you explained it very well. But I want to ask why there are two parameters under the same muscles.
Parameter.
Like if it's the same muscles, then the Q1 from Q4, their numbers should, I mean, at least to be the approximately close. But you said that it has a gap on it, does it? Or
Yes, you can see from the data, it's actually very different.
So-
I would like to explain this, maybe it's not clear enough.
yes.
Q1 is only the material impact, so you
Material
don't
impact.
consider others.
Okay.
And Q2 is while you only consider the stretch length when I inflate.
Okay.
And Q3 is while I consider the pressure with together with the stretch length.
Okay.
And the Q4 is only the pressure.
Q4.
There's actually the correlation.
Okay. I know the relation with bigger than 0 and smaller than 0, but what's the difference between your first the list calculation in the next page, the calculation in the next page?
Because I actually did different muscles.
Different muscles. So what's the
I
difference?
changed the balloon.
Change the balloon. On
Because I
what
want-
parameter?
What parameter?
Yes, like is it the size or just a different brain or different
They-
shape?
Actually, like different shape.
Different shape.
Because I want to talk about the geometry. The Q3 actually is affected by the geometry of the balloon.
Okay. So can you also if it's the different shape, then can you tell me in what shape it will exhibit what kind of characteristics?
Oh, that's why I took two of them. Because although they have different shapes, but the muscles still have the same features. Like the length, when you only talk about the length, it has positive correlation with the stiffness. And when you talk about the pressure, it's actually, both of them have positive correlation with the stiffness.
Okay. I know it's I can see that you want to use positive and not negative to exhibit that the muscles have the same feature even with the different shape. But the main point I want to ask is about the exact number. Like maybe on the Q2 part, it may be 0.4 in here, and sorry, what's the other number? Can we go to the next page?
Next page.
Yes, you have different
Yeah.
here, and here it's 0. It's a lot smaller. So, why does the shape cause this effect?
Oh, that's what we talked about in the previous discussion here. Because when the radius will become bigger,
Yes.
it will actually affect the length. But if the balloon's geometry is more like this
Mhm.
kind, the radius actually doesn't get so big. So the length can stretch more.
Okay. So, will you still consider it as can feature the air muscles? Because sorry. First, I want to ask, how do you consider a muscle work? How does the real muscles work? Because in this air muscle, I believe that the problem statement asks us to simulate the real effect of the muscle. So how do you think about it? How does the real muscles work? And what's the difference on your model?
It will become like this and it will shorten.
It will shorten? Okay.
Like this and this.
Yes. But under the length, under the longer shape of the balloons, its width
Let me
becomes
stop.
shorter, so makes.
So, you stop.
Oh, okay.
Yeah.
So during my discussion with the reporter, we discussed the different parameter and how does the manipulation of his experiments and figure out the few parameters in his equations. So that's our discussion.
So the opponent has 3 minutes.
Yes. So first question is for both reporter and the opponent. So since you mentioned about the muscle behavior, which parameters in the balloon do you think is the parameters for the muscle behavior? Is it the force? Is it the pressure? Is it the length difference? Which parameters?
I think it's on the length.
Length. So it's like the different deformation about the length.
Yes.
What do you think?
Affect the balloon.
No, which parameters do you think is the muscle behavior? Is it the force, the pressure, the length difference, or the net? Which?
The length.
The length. So okay, you
Oh,
both
wait,
think.
wait, hold on. Let me fix my phone.
Next question. So what do you think about the force? Do you think the force caused the force caused by the muscle is because of the balloon or the net component?
It's from the net.
The net. What do you think? Both. Both. Okay. If you can choose one, which one?
But they both have the force.
What do you think was the main cause of the force? Main cause?
The net.
The net.
Maybe.
Okay, so both agree on net. And so another question for the reporter: do you use Hooke's law to analyze the force?
No, I didn't use Hooke's law.
With there are variations about the constant.
I used similar formula.
Similar formula,
but
okay,
not Hooke's
okay.
law.
And so did you measure what shape do you assume is the balloon? Because in your graph, I think you input a calculation about the volume. So did you measure the volume directly, or did you assume the shape?
I
So
didn't measure the
You
volume.
did, okay, you
actually.
didn't measure the volume directly, then what do you assume the shape?
Assume.
Yes.
I actually had the balloon shape.
So
I did
what
the balloon.
the shape is that? Cylinder?
One looks more round a bit, and one
Or is it
more
eclipse?
longer.
So you assume, okay, so you use a cylinder, like a round cylinder as the balloon shape in your calculation, or you didn't calculate it?
The balloon shape is
Okay, next question. Did you consider about the fatigue of the balloon?
no because
No.
it will,
Okay,
I don't need to because I don't use it repeatedly.
okay. Then, about the pressure, so did you measure the pressure directly in the balloon?
No, I calculated it.
You calculated?
Because it's too small. If you see from the graph.
Okay.
Hard to measure.
So in the graph, I see the pressure goes up and then it dies down. So can you explain why is that linear, sort of linear relation and the decay?
Oh, because it's almost to its limits. It's also to
And why is it decay?
decay.
The pressure.
Because the pressure will actually fluctuate.
Okay, so it's a fluctuation. And since you mentioned about the stiffness in your key point, which part of your presentation is mentioned about the stiffness about the balloon?
The whole part is the stiffness because I
Which-
calculated it.
Which parameters specifically?
Q's, the 4 Q's.
Okay, time is up.
Thank you.
Review has 3 minutes, 2 minutes. Okay. The reviewer take the floor, the chance to talk.
Okay, so I'm the reviewer of this problem. And so for the pros and cons for the report, because there's no preliminary observation, so there's no comment on that. As for the theory, the report represents the relation between the F and the P, and the stiffness, I think is K, but and they show a clear graph, such as that graph. And however, I think they still have lack of theory, and they didn't discuss about the volume and the relevant parameters quantitatively, and they didn't express the relationship between them. Yes. As for the experiment, I think they are straightforward. However, they didn't conduct experiment about the K, and then there's no volume measurements, and as they mentioned earlier, and they didn't measure the pressure in the balloon directly. And then they have no experiment about the Q1, Q2, Q3, Q4. They just they think that it's positive, but they don't have physics meaning why it's positive right there. And for the analysis, they have explanation about the y-axis. However, there's no error in analysis, and there's no quantitatively discuss about the parameters, and there's no fitting about the data and the theoretical model. And for the Poland, for the presentation, I think you have a very clear speech, and it's easy for us to understand. And you did mention some of the key points. As for the short questions, you asked about the definition about the E, and then what is the force generated by the muscle. But however, you didn't come up and then do further discussions in the 12 minutes discussion. And you mentioned about the directional force, which you didn't further. I think you did further discuss about that. But for the cons, I think your short question isn't short and clear, and therefore it spends a lot of time to repropose it on the next section. And for discussions, you asked what's the muscle and the direction of the force, and you did have discussion about the experiment. However, you didn't dive deep into the discussion about the key point, which is the muscle behavior you mentioned in the short question. As for the discussion component, asked what do you consider the muscle like spring? And the report says the stiffness determined by length and the pressure. And we think that the report has no explanation about the relation, such as the decay, and there's no physical meaning. We cannot get a physical meaning from the report. As for the opponent, he asked what does the Q1, Q2 influence the muscle? They didn't say. They stand for this skip to the next part. As for the opponent, they asked a question about the experiment setup and how to measure the P, the pressure, and they use a tube outside, and then as the fatigue shows. But again, there's no direct measurements of it. And then what I asked is, what's the main cause of the muscle? And the opponent thinks both, but the net is more important. Reporters agree with the opponent, and I do agree it's the net, because if there's no net, the force wouldn't be that large as for the balloon itself. As for the volume, I asked about the assumption about the volume they consider, and they didn't have a clear image of how they calculate the volume, and we don't know what volume they assume. As for I asked for the fatigue of balloon, they didn't consider it because they say they didn't conduct the experiment more times. And do you manage to the pressure? Why didn't it decay? Because why does it decay? And they didn't measure the pressure. They can have no explanation for that. And this is the flow chart about this problem, because I think the opponent and the reporter both skip most important part, which is the physics meaning and the section of what causes the force to forward. So first, when air is pumped into the balloon starts to expand, and then before it attaches to the net bag, it causes volume changes, and the volume changes causes force, because it causes the net to deform, and that causes force. As for the static state, when the balloon expands to its next shape, and it causes the force to be maximum, and that causes this formation. Thank you.
Okay, so the reporter please conclude.
This is my concluding remark. We believe that the force is caused by both the net and the balloon, because you have to view it together as the whole muscle, not just caused by one. We discussed the whole mechanism. The parameter in the experiment is the property refers to the Q's, and I calculated the Q's and also the other data, and I substituted them into the formula. Opponent, I want to clarify something. The opponent asked, what is the force given to the balloon? It's a kind of force that the balloon conquers with the air inside the balloon. The property of the balloon didn't be told in the presentation. It's not the one the opponent hoped to see. We think that the stiffness of the air muscle can impact on the property significantly. The opponent asked, why is there a sharp growth and fall in the chart? It depends I did. How do you control the muscle work? I changed the radius. Is there fatigue? No, we didn't consider that. It's because we only used one balloon one time because so we don't have to consider the fatigue. But I did the experiment repeatedly with other. Thank you. That's all.
Okay. So it's time for jury members to ask questions. Any questions? I actually have two questions, but the first one I asked the reporter. So I just found to clarify. So can you show me the slide? I think 11, where you have a time versus 12. 12. So just definition of time and the LS, I didn't get it. You have the time, right? What do you mean by time here? I didn't get it.
Oh, the time between. It's like 2 seconds, and I measured it is this force. Because I filmed the process of inflating the balloon, and from the video, it's like the second is this force
Okay,
shown
so
on the
force gradually increase.
Yeah.
Okay. And what about the definition of LS? I didn't get it.
LS?
In your formula here, there's a L subscript S.
Yeah.
Yeah.
Sorry, LS is the stretched length,
Stretch the
while
stretch.
inflating it grows.
The change in length.
Yes.
Okay, I see. And so the other question is for the other teams. Reporter can also answer. So I guess the question, this problem has a balloon and a net, right? So in a sense, the question want to kind of simulate the muscle using these two stuff, right? This stuff. So what do you guys think? What's the essential ingredient of having a successful simulation of a muscle? Yeah. What's the required, for example, parameters? For example, right?
Can I answer?
Yeah.
For this.
You
Oh, okay.
can
I
answer.
think it's the length difference, the changing length.
So we need to be able to know why the change in length.
Okay, so because when we inflate the air in it, it causes the change in length, and then that length will cause the force to deform, will cause the force to happen. So I think it's the main cause is the length differences.
I agree with his points because in the real muscles, the mechanic of it, it becomes shorter and the width becomes the width becomes bigger. So I think aside from the length, I think the width is also a main point to be considered because like the two shape that the reporter says, he used one with with a long shape and the other I'm not really sure. I just maybe assume it's maybe close to a circle. Then for these two, its width expand differently for sure. So that will influence the exhibits of the whole muscle. So I will consider it would be the length and also the width.
Want to add to that?
Okay.
I
And
agree with the opponent. He actually said what I wanted to say.
Okay.
can I add something?
Yeah, sure.
I think I didn't mention it clear. When the length deformation, the deformation in length will cause the net deformation because the net is outside of the balloon, and the net deformation is the main cause of the force. So I think the underlying reason is the length deformation.
Okay. 6. So maybe
Maybe I ask one. So, reporter, can you go back to the first slide?
First slide.
No, second, sorry. Yeah, so here, the problem states that place a balloon inside a cylindrical net. So do you think, I mean for both three of you, do you think that cylindrical net is very important?
I think yes, because it will actually limit the balloon and it will cause the stiffness to increase because it's hard for the balloon itself
Okay,
to
thank you. So,
deform.
So as I mentioned on the previous question, I think the main cause of the force is the net deformation. So I think it's important to covers the balloon with a net, and because without the net, the force wouldn't be that significant.
Okay, I also with the both points, because the reason why I think the cylindrical is important, because at the beginning, if the muscle is not being pulled, the shape of it should be like a string, like it does not being pulled. But if it becomes cylindrical, it surely becomes wider. So this just exhibits the behavior of muscle just being wider, and it's exhibited by its geometrical structure. So cylindrical is, I think it's important.
Okay, so angle, time's up. So jurors, please prepare your score. Ready? So, if you're ready, please raise your score for the reporter. Order. Okay. 5, 3, 6, 5, 5. Okay. Now for the opponent. 7, 5, 8, 6, 6. Okay. Now for the reviewer, 7, 6, 8, 7, 7. Okay. Okay, so I think we conclude this round, right? So we can take a break for 15 minutes.